Hello and welcome to Lecture 9 of EME 172. So on Friday, Lecture 8, I covered the time response of second-order systems. This is material from Chapter 4 in sections 4.4 and 4.6. And so I talked about rise time, peak time, percent overshoot, and settling time. And specifically, I also talked about the categorizing second-order systems based on the damping ratio, right? So I talked about systems that are underdamped, overdamped, and undamped. So today I'm going to kind of recap the relationship between the second-order poles and time response. Then I'm going to talk about block diagrams, and I'll talk about closed-loop feedback. And so this is sort of all the material that you'll need to know to finish homework 3. I will note that there is a problem on homework 3 that talks about a DC motor, and I mentioned a DC motor having negligible inductance. And so you may be wondering where you get the model for that thing. So there is a lecture where I talked about DC motors and the equations for that. There's actually 2 equations of motion for the DC motor. The first one is an electrical equation, and the second one is a mechanical equation. And so if you look back to that lecture, you'll see the model, and it has the full electrical equation, including the inductance. And so what you're going to do in this problem is you're going to set that inductance equal to 0. Okay, so it makes the equation just that much easier. But anyway, that gives you an idea about where to start on that. Okay, so first I'm going to talk again about poles and step response characteristics. So if you remember from the second order system, second order transfer function, I said g of s is equal to omega n squared over s squared plus 2 zeta omega n s plus omega n squared. Okay, and I defined, so zeta is damping ratio, and omega n is the undamped natural frequency. And I defined something called the damped natural frequency, which is omega n times square root 1 minus zeta squared. Okay, and I talked about the time response characteristics of these second order systems and how it's related to the damping ratio zeta and the damped natural frequency omega d. So I'm just going to recap that a little bit. So if you remember, it turns out that the location of the second order poles in the S-plane okay, so here's the real part, and here's the imaginary part, j omega. Okay, and so it turns out that the poles are located here. Let me go ahead and mark them with x's, like this. And the real part of the second order poles, in terms of this second order transfer function, we can write this real component is minus zeta omega n, and the imaginary part is plus and minus j omega d. Okay, and the other thing that I told you about these poles is that they always will lie on a line here. There's going to be an arc with radius omega n. Okay, and actually let me write that down below here. There we go. Erase that little mark there. Okay, and then I told you that the last thing I want to tell you here is that this angle here, I'm going to call it theta. Okay, well, we can calculate this from, it's easy to calculate this angle when you think about what you know about this triangle. Right, so let me give myself a little bit more space here. So we have a triangle that looks like this. Right, so you know that the length of this side is j. Actually, that's not the side that we want, in fact. But we know that the length along here is zeta omega n here, and this length is omega n. So here's our theta. So we could write that theta sine of theta is equal to zeta omega n divided by omega n, or it's easy to see that zeta is equal to sine of theta. Okay? So that's how the damping ratio is related to the angle of the poles relative to the imaginary axis. Okay? So now let me summarize a little bit about how the pole location affects the parameters of the step response. Okay. So if you remember, the real part of the poles, zeta omega n here, determines the settling time. Okay? So all poles that lie on this line are going to have the same settling time. Line of constant Ts. Okay? And so if we look at the step response for this pole here, I'll draw it in green. Actually, I want to draw a little dashed line. It always helps for me to have a guide when I'm drawing stuff. So here's the step response. Okay, and I'll sort of draw an envelope. This is the decay envelope that determines the settling time, and so that decay envelope is determined by zeta omega n. So if I have another pair of poles that's on this line but further up, okay, so these poles correspond to, the way you can think about it is if I draw a line from the origin to here, right, that distance is omega n. And so clearly these guys are at a greater distance, and so this pole is going to have a higher frequency. The other way you can think about it is if I draw the line from the pole to the imaginary axis, that's the damped natural frequency, right? So I would get here, I get j omega d 1, and if I drew another line over here, I should probably extend my axis, j omega d 2, right? So that omega d 2 is clearly greater than omega d 1, so this response is going to have a higher frequency. But it'll still have the same decay envelope. Okay? So I'll say here that basically higher oscillation frequency, omega d, but same settling time. Okay? And so how this is relevant right now to your homework is if you're asked to find poles, closed-loop poles or open-loop poles that have a particular settling time, well, you know that you could draw a line along here, and all the locations that are on that line or to the left of that line are going to have a settling time that is less than or equal to the desired settling time. And all the poles that are over to the right of that are going to have a settling time that's greater than that. So they're going to be slower. Okay? So we could think about it. Let's see if I can fit this. So diminishing Ts, that's meant to say diminishing. And if we draw over this way, we'd say increasing settling time. So poles to the right of this line are getting slower, okay, and poles to the left of this line are getting faster. And any pole that's on this line will have the same settling time. Sorry, I'm not quite ready for that. Then the other thing we know is that if we draw poles like this here, so I'm going to draw the S-plane again. This time I'm going to draw a line like this, horizontal lines. Okay, so we have plus j omega d here, minus j omega d. Okay, and so if we have poles that are here, okay, it turns out that the peak time is going to be determined by omega d. So this line is a line line of constant peak time. So if we have two sets of poles, the green ones and the blue ones, their step response will look like this. Okay, so this peak here is TP. Okay. And again, what I can imagine about the blue poles here is, again, I'm thinking about the, it turns out that they have the same oscillation frequency, but the blue poles, because they're further into the left half plane, they actually going to have faster settling time. Okay, so they have a greater damping ratio. The other way we could think about that is that if we think about the damping lines here, right, that clearly this one is moving to larger angles, and so the greater that angle is, the greater the damping ratio is. Okay, so it will turn out that the blue response, the blue poles, have the same peak, but they're going to settle faster. Okay, lines of constant peak time. And the last thing that I want to show you is a line of constant damping. Okay, so any poles that are on this line are going to have the same damping. So if I draw some green poles here and some blue poles over here. Okay, so what's different about these poles? Well, they have the same damping ratio, but if you, again, think about the natural frequency being the radial distance to the origin, it's clear that, that the blue poles are going to have a higher frequency than the green poles. Okay? And what does the damping ratio govern in terms of the time response? Well, it turns out that zeta determines the overshoot. Okay, so percent overshoot depends only on zeta. Oops. Okay, and so we can sketch time response here. Let's see, once again, I need my little steady state line here. So the green one, he does this. And the blue one, well, he's actually got both a higher frequency and also faster settling, but it's going to have the same amount of overshoot. So the blue one's going to sort of spike up like this. Same percent overshoot. Okay? So in other words, if you're asked in a design problem, if you're specified, the percent overshoot is specified, then you can immediately determine the damping ratio zeta, and so that lets you know what line these poles are going to lie on. Okay? And in particular, if we kind of go back to any of the other requirements that we have, if we specify, so like the constant peak time gives us some horizontal lines, the zeta gives us these radial spokes, and the settling time gives us these vertical lines, right? And so any two of those specifications taken together would specify a unique pole location, right? So if you imagine that we're given sort of some specifications about settling time, that would give us a line like this. And then a damping ratio or percent overshoot would give us a line like this, and the settling time would give us a line like this. TS specification. Okay, and this one is the percent overshoot specification. And so together we end up with a unique location for the pole. And the same thing is true if I give you a settling time spec and a peak time spec, right? Because that would give us a vertical and a horizontal line, and taken together they will have one intersection. Okay. Now it's also possible that